Welcome everyone. Thanks for coming to this seminar. It is great that we have Shukla Poddar to give us the seminar today. Shukla studies the impact of the climate change on the PV generation, and her recent study involves the module degradation. She finished her PhD from SPREE, and recently he worked in arena project in SPREE to continue her work. Today, her topic will be what does future of photovoltaic generation in Australia look like. So the stage is yours. Thank you.
Thank you, Kaiwan, for the introduction, and thank you everyone who has joined here. So I will be talking briefly about what I have done for my PhD, and kind of it looks at the different future scenarios and involves climate modeling. So I guess the title was a bit fancy and everybody wants to know what the future holds like. But unfortunately, I'm not going to do this sort of psychic stuff or do tarot card readings and tell you what the future is. Instead, what my work is, it's kind of a lot of data crunching, data science, complex climate model, and kind of projecting what is going to be the energy yield in future. I'm pretty sure lots of you here have already lived some of these few incidents, and others have seen these horrific images probably in the news and read lots of articles about it, starting with the extreme dust event in September 2009, then the bushfire period 2019-2020, then we had extreme rainfall accompanied with floods, and then of course the last one is where Australia made a highlight. It was the largest hailstorm that was seen in Queensland. And all of these events are somehow connected to the extreme events that we are seeing in our climate right now. And they have kind of impacted the amount of energy generation, they have damaged the materials, and not to mention the energy yield, and also affecting the life of lots of humans. But what I want to say is climate and meteorology go hand in hand with the energy generation, and specifically when we are looking for something like PV. So this figure here kind of tells you what are the different events that could impact the productivity, and what type of forecasting skills we need in order to kind of understand the impacts. So there can be like small events like lightning or cloud movements throughout the day, or even like thunderstorm and hailstorm that can affect and impact the amount of energy generation, and at the same point of time it can also lead to a lot of material damage. So if we do a day-ahead forecast for these sort of weather events, it might be useful if we want to control the stability of the grid, or if we want to do some energy trading. Looking at a seasonal or a synoptic scale, these events, there might be some extreme weather events that might occur periodically, and if we are kind of prepared, or we know what is the frequency of these sort of events, these might be also useful if we are trying to look for a new site, proposing a new solar farm, or if we want to do some material selection, or even resource assessment and planning the storage. Then comes the climate projections, where we talk about what is happening in decadal and multi-decadal variability. And these are kind of the large-scale events that occur because of the changes in the atmospheric and the ocean circulations, kind of changing the cloud cover, the atmospheric aerosols, and also the amount of solar radiation that directly impact your amount of power generated from the PV. So giving you a taste of what sort of forecasts we kind of require and which areas we are trying to focus on. So all my next few slides would be kind of looking at the multi-decadal and decadal projections, because we are more interested in what's happening and what is going to happen by the end of the century. Again, lots of solar experts, and everybody is quite familiar that the installed capacity of the renewables have increased, and this figure kind of shows what is the increase in the percentage from 2012, and Australia has done quite well with 48% increase in the capacity, net installed capacity. So recently we have also seen that the energy generation in Australia has increased, and renewables have contributed a lot to it, and the growth being exponential instead of being linear. Last year itself, we had about 36% of the total electricity being supplied by the renewables, out of which, out of the total electricity, it was 14% approximately that solar contributed. Having said that, the future of solar in Australia is bright, and we are kind of moving towards that space. Also, IRENA has, this figure from APVI that shows the number of PV installations, and that has also increased over the years, and again the growth not being linear, it's kind of exponential. And we are also forecasting that that we are going to follow this sort of trajectory or roadmap for the future, where we are going to have more renewables with solar integrated in it. But since the amount of energy that we are kind of extracting from this, from solar PV is kind of dependent on the climate and the weather parameters, not to mention radiation and clouds being most important, but there are other factors like wind direction, your temperature, your humidity, what is the amount of aerosols, if you're having dust, and so on. So this kind of makes it susceptible to the future climate change. And CSIRO kind of has recently released a report in which they have already said how much temperature we have exceeded from the pre-industrial levels, and we are already at 1.1 degrees and more than that. So in this figure graph over here, you can see a big range, that is the region of uncertainty or region of that can be a probable future in future forecast, this yellow ones, and the mean line shows what has happened historically over the years. But these expected changes in temperature are kind of dependent on the amount of carbon dioxide that is expected to be emitted in the future. So IPCC kind of releases these different climate scenarios in which we simulate, or which different climate models that have different carbon dioxide concentrations. So the famous four, that is RCP 2.6, 4.5, 6, and 8.5, they are the different trajectories that we can take possibly in the future, with RCP 2.6 being the most optimistic scenario, where the mean temperature change is going to be up to 1 degree Celsius by the end of the century. The most pessimistic being the high emission scenario, where the mean temperature change is going to be 3.7 degrees Celsius. But there are also other intermediate scenarios like RCP 4.5 and 6, where the mean change is going to be up to 1.8 to 2.2 degrees Celsius. So all these scenarios kind of take into account what sort of climate policies we are going to adopt, what is the amount of renewables that are going to be integrated, and how much carbon dioxide are we going to cut off. So having said that, this is the future projections for the temperature, and we can see that the spikes are obviously going upwards. And unfortunately, last year, the report from IPCC kind of said that we have already crossed a limit of 1.1 degrees Celsius. So we need lots of climate policies to be integrated if we still want to achieve the Paris target. So with these changes in the climate conditions, there comes the risks. With the increase in more frequent extreme weather events, we can have power outages, and that can lead to complete blackouts, or there might be complete change in the atmospheric circulation that would result in changes in cloud cover and changes in the amount of radiation that would lead to, again, more frequent power losses. There can be a variable resource, or and also we can have more enhanced module degradation because of these extreme sort of climates that we are expecting in the future. So this is where my PhD comes in, and I have looked at the different aspects of what the future of solar PV is going to look in Australia, considering the different climate scenarios and climate projections. So for the first and the second part, I have looked at the weather-induced variability, looking both at the resource variability and what is going to be the variability in terms of the power projections. Then I have looked at the long-term changes in the PV potential and what are the different drivers. And then the last part is looking at the role of climate in the module degradation. So for all my work, I have used these climate model projections. So giving you a taste of it, the entire climate, in a climate model, we kind of divide or dissect the entire Earth into different horizontal and vertical grids. The horizontal grids constitute of latitude and longitude, and the vertical grids are your pressure levels. So what happens is in these small grids, we kind of feed in the variables, either taken from your historic observations or from your reanalysis data sets or from the satellite, and then we try to forecast what is going to happen in the future. So each grid cell is able to simulate what is exactly happening in the Earth in terms of all the physical processes, in terms of your atmospheric circulations, in terms of your ocean eddies, ocean currents, how the feedback is, what are the different interactions. So they are kind of replicating what is exactly happening in this in that particular section of Earth. And this is how the complexity of the model looks like. Over the period of time, the modeling community have kind of put their best skills to enhance and replicate the Earth's climate so that we are having more confidence in the future projections, and we are kind of able to say with confidence that this is what we are expecting in the future. So the modeling has of course started from 1960s, but now here when we are able to entirely simulate the and replicate all the different processes occurring in the Earth, even including the sea ice extents and how they are varying and changing in the ocean. So there are two different types of climate models. One is your global climate model that kind of simulates and gives you what is happening in the entire globe, and then comes these regional climate models or this limited area models. So you can just imagine the difference is just like a picture. So if you're increasing the resolution, you're able to see a better picture of what's happening. So it's just the same thing. The pixel size are increasing, or that means the number of divisions, the horizontal and the vertical, are increasing in the RCMs, as a result of which you are able to simulate the subgrid scale processes. So for example, there is a convection, a sudden thunderstorm happening at one area. Your global climate model will not be able to give you that idea of that's going to happen or that has happened. But your RCMs, on the other hand, they can simulate those extreme small events that has also happened in those small grid scale processes. So I have used the models from Cordex framework. So what happens is, this is a global initiative from the different modeling groups across the world, where they kind of run these regional climate models over different regions. And I have of course used it for Australia, called the Australasia projections, that has been run over a period of 100 years. And these projections are again run for the different RCP scenarios that I showed you in my previous slide. So the models in this RCMs, they are having a spatial resolution like up to 50 kilometers, and some of them are even up to 20 or 25 kilometers. So it just depends on the number of grids you are choosing and how you are running the model. But as you increase the number of grids, of course, your computational speed and your time is increasing. So that's always a trade-off where you want to kind of select the best both the things. Again, since we are talking about the future, there is going to be a lot of uncertainty, and the common question that people ask, how are you going to say with confidence that this is what's going to happen? So we have performed this grid scale confidence tests or t-tests at every grid point, where we have taken a bunch of climate models, for example, up to 15, and then at every grid point we kind of analyze what is their significance, and then we have this color coding scheme where we say if it's significant, that means 50% of the models show that the change is significant, and 70% of them are agreeing in the direction of the change. So 70% either agree it's going to be increase or it's going to be decrease, and then only we use the dots. Then there is insignificant agreement, where less than 50% of the models kind of show significance, and we have less confidence that this is going to happen in the future, and it's completely in color. It has no dots in them. Then there is this significant disagreement, where 50% of the models show a significant change, but out of those 50, 70 of them are not agreeing in the direction. So it means that there is going to be some change in the future, but we are not sure if it is going to be a positive change or if it's going to be a negative change. And that's where we have used this white patches or blobs. So the first part was looking at the resource assessment and solar viability in Australia. Australia has a lot of sunshine and a huge solar resource because of its geographical location, the north being having the highest amount of radiations. And also this figures on the right kind of shows what are the existing solar farms, and what are the proposed as well as under construction solar farms. So if you can notice, the pattern looks like it has everything is kind of shifted towards the east. It's just on the eastern side of the continent. And so just remember this thing. We will, when I'm talking about my different results, I would be highlighting it and pointing back to what we are expecting in the future, where we are going to have more number of solar plants. So first we wanted to kind of look at what is going to be the solar resource reliability, and we have used matrices like availability and episode lengths that kind of says what's going to be the duration or how many number of hours we are expecting there is going to be sunshine, that where we can capture or we can get efficient amount of solar power at that location. And again, it kind of replicates back to the mean radiation figure, where we have higher availability near the north because of the geographical location being closer to the tropics. But when we look at the mean episode lengths in the historical period, we see that the patterns are varying a little bit, higher blobs near higher amount near the west and some near the northern and the central regions. Then we wanted to look at how these are changing under a very extreme high emission scenario. So for my different studies, I have included different emission scenarios, and somewhere we even compare the scenarios, because for adaptation and reliability studies, we kind of want to have that huge range where we want to know what can be the wide uncertainty range and where we can like kind of wobble around. So I have looked at in the two periods, that's the near future and the far future period. And if you just look at these black circles, these kind of say these are the regions where we expect higher number of solar farms in the future, and also these are the regions where we are expecting that the resource reliability in terms of more efficient available power and episode lengths are increasing in the future. So again, we want to say that the power supply is going to be more reliable in these regions of Australia. The second thing we want to know is how intermittent the resource is going to be. So we kind of define lulls. Lulls are the periods where you have no energy generation. So these lull periods do not include your nighttime as there is no power generation. So these are the periods during the day where you have just complete no generation, and probably that's because of the cloud movements, or if it's a completely overcast day. And again, we can find that the mean lulls are more towards the south, and towards the eastern region are the maximum lulls. Looking onto the future, we find that these mean lulls are kind of decreasing over the east, but the maximum lull periods, they do not have any particular sort of pattern. They are more scattered, with some places towards the east and towards the north being where we find the increases, but mostly they are decreasing along the eastern part of Australia. And this is where we kind of looked at why this sort of patterns are happening. So we wanted to look at what is the reason behind these changes in intermittency and changes in the reliability. So we find that the number of clear days are increasing in the eastern regions of Australia and decreases over the west, while the number of intermittent days are decreasing in the east but increasing over the west. So this kind of gives us the picture and says what's happening on a daily scale basis, where you have number of cloudy days decreasing in the east with increases in the west. But now we were also interested to look at what's happening in the different hours of the day. Is the intermittency increasing or is it decreasing? Because that dynamic relationship is very important if you are a grid operator, because you want to maintain a stable grid supply. So that is where we kind of looked at the solar power ramps, and on a clear sky day, we expect that the power output is going to follow the normal diurnal curve, a GHI diurnal curve that's very clean, and you are able to predict it. But on an intermittent day, we find that there are fluctuations in the power supply, and these are mostly because of the cloud movements. So whenever there is a sharp increase in the power, it's known as a up ramp event, and when there is a decrease, it's known as a down ramp event. So we used this modeling tool from PVlib in order to simulate the power supply. This is also because since the climate models are computationally expensive, they do not save all the different outputs, and the main output that would be saving is like globally used by different people. So we had to kind of get our diffuse and direct radiations. We also had to then generate the plane of array irradiance, and then use the power conversion models using PVlib to generate or to get the model power. And we looked at the different technologies, looking at the curves, if curves are fitting or not, and they were looking very good even for intermittent days and even for a completely clear sky days. So we looked at the power ramps, and there are three important characteristics of when we talk about ramp. One is the magnitude, the second one is the frequency, and the third one is the duration or the amount of time in which the ramp is going to stay. So looking at the historical period, we found that these ramps have a higher magnitude mostly near those eastern belt, and we associated that with the east coast lows and frequent cloud movements in those regions. When we talk about the frequency, we see that the higher frequency ramps, like the more frequent ramps, are occurring near the northern part of Australia, and they kind of decreases as we move down. But the most surprising thing was the ramp period. We have a longer duration ramp existing always near the eastern part, again because of the extreme high cloud movement activity in these parts rather than the rest of the continent. So we were interested in looking at how are these changing in the future in different periods and in different scenarios. So I am showing the results for the end of the century for two different scenarios, RCP 4.5 and RCP 8.5. So this paper was mostly targeted to kind of help the grid operators. So we had to compare the simulations between different scenarios where you also include climate policies like in RCP 4.5, but RCP 8.5 being the most negative, where you don't have renewables, where you don't have any climate policies included. So the ramp magnitude is decreasing in the future. That's a very good thing. But at the same point of time, we see that the frequency changes are very dependent on the location. So we have regions where they are increasing in the increasing frequency, especially these green blobs, the green circles. And these are the regions again where we are going to have the highest number of solar plants in the future. So that means there is going to be more voltage flicker issues, and we might need more investments and careful ramp control devices if we want to have a stable grid supply. Then when we look at the ramp periods, we again find the regions, these same regions have increases in the ramp periods. So what we are trying to say that the eastern regions are having increase in frequency of ramps and also prolonged longer duration ramps. So kind of that means there will be extended periods of energy deficits. So doesn't matter what does it look like in a daily scale, the variability can change in terms of an hourly scale. So the variability is kind of dependent on different time scales in which you are looking at, and this is a reason that we have explored the different time scales and different temporal resolutions, how they are going to change. Having said that, we were very interested in looking at the long-term future projections, what is going to happen by the end of the century. And these are this was looking at the PV potential, and we have used crystalline silicon cells in order to look at this PV potential. So what's going to happen is, what's happening in the historical period is we are seeing the highest PV potentials near the northern and the western regions of Australia and kind of decreasing towards the south. Again, the geographical location being one of the reason. But in the future, when we look under a high emission scenario, we find the PV potential is expected to decrease almost throughout the continent, and these changes are going to be significant. Well, it's just 2%, so people might ask, why are we interested? But that 2%, if you just convert it, it's going to be in some hundreds of gigawatts. That is important. So that's why this 2% is also significant, and 2% is also important. So the reason was, why are we seeing these changes? So we did some sensitivity experiments and analysis when we try to disintegrate and see what are the different variables that might play a role and why are we seeing these changes in the future. So we looked at radiation, temperature, and wind speed, and we expected at the first that it's just the radiation, changes in the radiation, that is driving the changes in PV potential. But later on, when after we conducted, after these experiments were done, we were like, oh no, this is temperature. Temperature is playing an important role, and we are of course seeing this sort of changes in the PV potential because we are expecting a higher temperature. So when your module is having a high temperature, the efficiency of the module is decreasing, as a result of which we see there is a long-term decrease in the PV potential. So we kind of looked at the different we kind of looked at the cell temperature, the mean as well as the maximum, and we find that the mean temperatures are both mean and maximum are increasing in the future. The increases can vary up to 2.5 degrees for mean cell temperature, while the maximum is changes are up to 8. And these regions are very significant, so we are highly confident that this is likely probable in the future. So this then leads us to look at if your module is experiencing higher temperature, so is it going to degrade or not? So that's when we looked at the different degradation modes and mechanisms and the role of climate in it. So we identify the 3 important climate stressors, that is relative humidity, temperature, and your UV radiation, and then look at the 3 different mechanisms, that is hydrolysis, thermal, and photodegradation. These degradation mechanisms, either by itself or in conjugation with the others, kind of lead to the different degradation modes. And and the room is full of solar experts who are expert in these reliability aspects. So I'm not going into greater details of explaining each of the mode, I'm just showing the results. Then we tried looking at these mechanisms, degradation mechanisms for monocrystalline silicon modules and how they are changing under both a low emission scenario and under a high emission scenario, RCP 8.5. And these changes are shown up to the mid-century. So we expect that the hydrolysis, in the historical period, we see that the hydrolysis is kind of higher near the northern regions. These are northern regions of Australia, but the thermal degradation, we find that they are higher more towards the west and more near the central and the northern parts. But since photodegradation mechanism is kind of dependent on both relative humidity, temperature, and the UV radiation, we find that these are high for the northern parts of Australia. Looking forward in the future, we see that these degradation mechanisms are expected to increase in the future. And again, as I mentioned, all these dots kind of show how much confident we are about this thing happening in the future. So we have looked at the different degradation modes, but I'm just showing one here, delamination. And the figure on the left kind of, so delamination, I think everybody knows, but still I'm just repeating it. Delamination kind of occurs because of moisture ingress and also high temperature. And we see that the delamination is high near the western and the northern regions of Australia during the historical period, but looking forward in the future, we find that this mode of degradation is going to increase, again highly significant and highly likely probable in the future, with higher changes expected near the northern and some central regions of Australia. So at the end, there were a couple of other degradation modes that we have looked at, but at the end we kind of came up with the total degradation and its degradation rate, and this total degradation rate was based on the probability of occurrence of each of the degradation modes. So again, each of these degradation modes can have different probability of occurrences based on the climate and based on the weather in which they are exposed to. So we have considered that, and we followed a Copenhagen climate classification, and that's why, and that's what we see, that the northern and the eastern regions of Australia are expected to have a higher degradation, and again, these are the same regions where we expect the higher changes in the future. At the end, we also looked at what is it going to have an impact on the LCOE. So our study includes the cost changes that they are considered constant, and we are not considering that they are changing in the future. And we find that the LCOE is again going to increase, and increases maximum on those regions where we find higher total degradation rates. So having said that, just wrapping up and kind of saying what are the current challenges. First is there is a huge uncertainty range in whatever model projections we are using. That is because each climate model has its own independent behavior that is complex in itself, and it needs to be understood. The second thing is high temporal resolution. So climate models kind of give you usually hourly data, but if you want to look at extreme events or what's happening in the short term in terms of minutes to seconds, you need to run your own climate models to generate that sort of data set, and that is again computationally expensive and requires a lot of storage. The third thing in terms of degradation is the probability of occurrences of these degradation modes might change in different regions depending on the changing climate and depending on the exposure levels. So it is difficult to model all those things. We need to have a complete framework, disintegrate them into string level, do those sorts of analysis to come up with a more robust degradation modeling framework. And some takeaway points. We need more site assessments that include climate change and climate change related studies when we are looking for new sites. We also need to think about adapting towards these events or these probability of occurrences. So we might need to think about what we should invest or which devices we need to have in order to have a stable and a reliable grid supply. And then we should also do comparative analysis between the different PV technologies, because there are some technologies that do not react to high temperature that much. So my study was limited to crystalline silicon, but it should be expanded to look at the different technology analysis as well. And then the last thing, which is very important as well, to look at the coexisting renewable technologies at the same farm, like solar and wind existing at the same place. So future directions. I'm kind of working on the modeling module degradation, coming up with a better projecting model, looking at the clear sky classification schemes and how to distinguish the different variability occurring during the day. Then something that I'm very interested in is extreme weather events and how they are impacting the energy generation. And also this is one aspect that I would like to explore, that is co-located solar and wind farm. What are the possibilities, future challenges and risks? And this is the wonderful team. All the hard work was just not mine. It was a lot of hard work, a lot of discussions with my amazing supervisors, and special mention to Coco. Yeah, thank you, and happy to take questions.
Thank you, Shukla, for the very interesting and impressive talk. Do you have a question for Shukla? I may have one to
Gavin.
Okay, Gavin.
Very nice presentation. Thank you very much, Shukla. Excellent. Yeah, I had a question on the PV potential. You estimated the potential, and I think it was over the next 20, 30 years, there's going to be a reduction, which you explained is due to the reduction in, the increase in temperature. But did I read it correctly? That out towards the end of the next 30 years, it's going to be, it's still decreasing. Sorry. Oh no, I think I was looking at the sort of inland eastern Australia. There's some red parts there, which are presumably an increase in potential there. What's the reason for that? Is that also a temperature effect, and is it a decrease in temperature?
If you mean these regions?
Just to the left a little bit. The sort of looks like the sort of in a New South Wales and in a Queensland.
You're saying that those regions are decreasing, and those are the highest decreases in the.
Oh, are they? Oh, okay. I'm misreading the colour coding. Okay. Okay, so that makes sense. So it's a temperature effect primarily. But then in your next slide, or the next but one, I think, you were talking about the temperature effect. I think it's the next slide. And yes, this one here. So the effects of temperature are primarily in the north, which makes a lot of sense. And this is on, my question is this actually on module degradation data? So the actual data, or the prediction of the module degradation?
So this is just on the predictions based on the climate model data set that we have used using some statistical models to kind of simulate what's going to happen for crystalline silicon. Okay.
And is it just temperature, or is it also humidity?
That's what we are actually looking for, the degradation modes. So we find it's a combined effect of humidity and temperature, and but again, those are very much region dependent. So we expect like high temperature and high humidity, for the northern parts over here. But like again, it's dependent on the location where you are trying to actually figure out what's happening, because the relationship is not very linear. It's
yes, I agree. Okay. Thank you. Okay, thanks very much. Thanks for your presentation. You showed that the LCOE is expected to increase quite substantially, up to 10% over the next decades. Maybe you could comment, is that mainly due to sort of failure mechanisms, or is it mainly due to temperature effects? For example, the normal effect that power generation is lower at higher temperature. What is the main contributor to that, in your view?
Yeah, thank you for your question. So I might have not explained that very nicely when I was talking. So the LCOE the LCOE changes that we are expecting here, it's completely based on the module degradation. So just so if we just expect that there is going to be module degradation, we are expecting that the changes will be up to 10%. So we are not considering any other changes in the market or volatility or anything. And again, yes, to answer the second part of it, it's mostly driven by temperature changes.
But degradation, you mean the actual performance of the module degrades, or is it so you're not taking into account the normal effect that a module provides, generates less power at higher temperature? That's well known. So if you consider 2 or 3 degree temperature increase over the next couple of years, you would expect that power would be lower.
Yeah.
Is that included or not?
Yeah, that's included.
The other comment I had was on your degradation mechanisms. It looks like you've included a lot of sort of catastrophic degradation mechanisms like delamination and so on, but whereas for the normal degradation mechanisms that occur over time, which are sort of considered normal power losses, I think you only had PID, whereas there is quite a large number of other mechanisms such as LETID, LID, and these mechanisms actually lead to a degradation first and then a recovery. So I'm wondering, have you included that in your modeling as well?
No, that unfortunately I didn't look at that. So we just included delamination, corrosion, cell ribbon, and the cracks. So the others are pending. That was like my last part of my thesis, so didn't have really time to explore all the other different aspects.
Hi. Thank you for the presentation. It's probably just because I'm not familiar with these methods, but the sensitivity analysis that you did to identify that temperature was sort of responsible for a lot of the degradation of the PV potential. Like, how do you do that kind of analysis?
So we kind of disintegrated and broke the entire complex equations, looking at different climate variables, keeping some constants, and then kind of coming up with that.
I may have another final question. In the future suggestion, you said that we need to consider the coexist multiple renewable technology in the same farm. Can you please comment that? Is that because like the solar, the wind renewable energy is less affected by the climate change, and they can solar can work better when or winter can work better when solar farm is not working as predicted?
So there might be like intermittent periods during the day when you, like for example, if there is a complete overcast, your solar farm is going to generate very less. But if we had wind at the same point of time, we can supply the energy deficit because from the wind, extracting from the wind, so you can have a more stable and a reliable supply instead of just having one renewables. So it's just based on that. But we haven't done any climate change studies on wind yet, so that's something in the future.
I don't know if the climate change also affect the wind farm, the same chain as you the solar farms.
That's something we are planning to look in the future.
Okay. Thank you.
Thanks, Shukla. I'm going to go to Torsten's question as well, because this is of all the data you've presented, this is the one that has the most significant change and potentially a significant impact on investments in markets around the LCOE. Have you published this result yet? I notice you've got a paper there.
It's still under review, so yeah.
All right. It would be really interesting to look at those degradation mechanisms to see how they're modelled and what you've considered. because so are you doing time-based modelling, right? Because clearly the modules, the panels aren't at the elevated temperature all day, every day.
Yeah.
That's all in the models. It's all time, so it's done in 5-minute breaks or something like that. So if it might be 2 degrees hotter than it would have been in 20 years' time. So you're already modelling that it's at 65 degrees, and you're saying it's going to be at 68 degrees. Is that what you're saying? And therefore the degradation is accelerated by those extra few degrees. It's not compared to no degradation.
Yeah, thank you, Renata. But we are also looking at how they are varying with time as well. So it's not just it was 65 and it became 65 after 2 years or after 10 years. We are also looking at if that 65 was 63 as well and then became 65, because there might be some events where, or like during the span of the day, it can cool and then again it can heat up. So we are including all that as well.
Yeah, would be good to. I'm not an expert on degradation, but I think we've got some real experts in the building, so probably really good because it's such a significant finding, which will, if people take it on board, that'll affect investment decision making. We ought to be really comfortable with it.
Okay, if we don't have other question, we thanks Shukla again for the interesting talk.
Thank you for joining.